Hello to everyone. In last lecture, we have discussed about the diatomic molecule as a harmonic oscillator, that is a vibrating spectra. Now, in this lecture, I will be discussing about a diatomic molecule as anharmonic oscillator. So, if the experimentally observed infrared spectrum from the diatomic molecule, which is treated as a harmonic oscillator, it shows that it is a disagreement with respect to our harmonic oscillator, because if you have a harmonic oscillator having a single frequency omega, that is a fundamental frequency omega, then there must appear a single band. However, single band at a frequency omega centimeter inverse, which is a classical frequency of vibration of the molecule. The actual infrared spectrum is, however, found to consist of an intense fundamental band at omega plus a number of weak bands, that is called the overtones, at slightly lesser than the 2 omega or the 3 omega. So it means that these overtones indicating that the selection rules delta nu is equal to plus minus 1 is not strictly ovate, and the transition corresponding to delta nu greater than 1 do take place. So this is attributing to fact that the dipole moment of molecule is not strictly linear with respect to their intermolecular displacement, that is x is equal to r minus re. This is expressed as the electrical anharmonicity of a molecule. The observation that the overtone appeared not exactly at 2 omega, 3 omega, but at a lesser values indicates that the vibrational energy levels are not exactly equally spaced but converging slowly. So this attributed to the fact that for an actual molecule, the potential energy curve is not strictly parabolic except the near lower energy levels, near the minima, that the potential energy function V of R is not harmonic. And so it means that we have to model this potential VR. In terms of this, we have to expand in a Taylor series so that we can include few higher order terms, quadratic terms and cubic terms. So even that if you are taking that the cube term, again it will be providing a more appropriate analysis of this diatomic molecule for the vibrational spectra. So the first approximation, let we include the cubic term so that this VR is equal to 1 plus of 2 dVy, because the first term, because you have R minus Re at R is equal to Re, that will be the 0, the first term is not here. So this is 1 upon 2 factorial del square VR divided by del square at R is equal to Re, this R minus Re whole square plus of this one. So now we are defining these terms, this f of Re, because the rest of the quantities are the constants, and this f R minus Re square and z R minus Re cube. So we are defining this as a function of x square, fx square and gx square, where obviously this g will be very, very less than to this f. So once you are substituting the value of this VR in a Schrodinger equation and solving that the very tedious mathematics algebra, to find this using the perturbation theories, once you will be solving out all this stuff, at this juncture we do not need to find out the solutions of the eigenvalues of that Schrodinger equation for the anharmonic oscillators, and directly we are giving the eigenvalues of that harmonic oscillator. Then this appears to be this E of nu is equal to hc omega E nu plus of half minus sc omega E xe nu plus of half square and so on. So the corresponding terms values are given by this z of nu, this E of nu divided by h of c. Just that is the wave number we are giving that. Then we have g of nu is equal to omega e nu plus of half minus omega e xe, or nu plus of half is squared. Now this quantity omega e is the spacing in centimeter of energy levels that would occur if the potential curve were parabolic. So if I have a parabolic curve, then the frequency is omega e, that is a wave number. On the other hand, this term omega e xe is a anharmonicity constant, which is much smaller than, and they always positive. This quantity is positive and very small. The equation number 2 shows that the energy levels of the anharmonic oscillator are not equidistant. From this lesson, if you see, because once this nu is increasing, this is a non-linear relation. It is not a linear relation because this is a nu plus of half c square. So it is a non-linear. So if it is a non-linear, it means that simply their spectral, their bands are not equally separated. So, and they are slowly decreasing because the value of, because this is positive quantity, it won't be this positive quantity, positive will be appearing here, it will remain the negative, then this nu is increasing, then this quantity is decreasing rapidly. So now it is not a very perfect parabolic. If you look at for the lower minimum energy levels, it is a parabolic. As we are increasing, then this parabolic behavior is no longer valid. Now if you look at their energy levels, slightly are different. Means it is gradually decreasing. At a certain level, you have a discrete energy levels up to the dissociation energy level. After that, you have a continuous bands over here. You have a continuous band over here. And in that case, now once it is dissociate, then you have the atom are completely separated, and once they are completely separated, then these atoms get gaining that the kinetic energy, and that is why you have a very continuous spectra over here. So the outermost level is connected with your continuous energy band. So when a molecule receives energy more than the corresponding to the uppermost vibration level, it dissociates into atoms, and the excess energy appears as unquantized, because once I'm saying that the continuous, that is unquantized, the kinetic energy of atoms. So hence a continuum, the continuum joins the uppermost level. The 0 point energy of the anharmonic oscillator is obtained by putting this nu is equal to 0 from equation number 2. Then just putting this one, then you have this 1 upon half of omega e minus 1 upon 4 omega e xe. If the energy level is referred to the lowest level as 0, so what we are saying that it is a 0, it means that then the equation 2, if you look at equation number 2, it is a 0. Once I am saying that this is the 0, means that is half factor we are not considering, simply this. So then I could write this omega naught, this we are representing omega 0 of v, omega 0 of nu minus omega 0 x0 and a nu square. Equation number 4. On the equating the coefficients of like power of nu in equation number 2 and 4, we now once we'll be comparing the equation number 2 and 4, then so this omega e, here you have this omega naught is equal to omega e plus this omega is coming from over here, this 1 omega is coming from here. Once this is the squaring this omega, this nu square plus of 1 upon 4 plus of nu. That nu once you are multiplying, that is your minus omega e xe. Then you have this term. This omega naught is equal to omega e minus this one. And for the square term, this omega naught and x naught is equal to omega e xe. Then you have this term compared to this term. Then in this case, you have the square term of, because we are taking only the second order, then you have this omega e square and x square. So then this is equation number 5. I think it is clear to you now. Let us now investigate the infrared spectrum for the enharmonic oscillator. Since the eigenfunctions of the enharmonic oscillator are very similar to that of this harmonic oscillator, then the selection rules were obviously using that delta nu is equal to plus minus 1. It still holds, giving the most intense transition, that is the fundamental. It will be providing for the delta nu is equal to plus minus 1. In addition, for an enharmonic oscillator, there are transitions corresponding to delta nu plus minus of 2 plus minus 2, 3 can also appear even though with a rapidly decreasing intensity. The possible transition absorption when all the molecules are initially at nu is equal to 0, that is a stable, that is a ground state. So now if there the transitions are taking place, now only this one, not only the 0 to 1, only the now this one level to third second excited state, second excited to the third excited state. Now in this one there is a, because the separation is equal but it is not the equal one, so what should happen, that is if I have this is the fundamental one, then this is slightly higher as compared to this one, as compared to this one, as compared to this one. This gap is not equal, rather the gap is slowly decreasing. Because if you look at what we are saying, that these overtones are we are achieving, but intensity is less, that is a converging, but it's not directly this 2 omega, 3 omega, 4 omega type of the relation. There is a lesser to the 2 omega, lesser to the 3 omega, lesser to the 4 omega. Means that there is not a equidistance or equal separation between these energy levels. As because mu is increasing, you have this positive quantity over here, then this is a positive quantity over here, then you are not getting the equal distance or equally separated energy level. So this separation must be the this is not, it is appearing in as equal, it is not equal, rather this is the biggest one, then it's the smaller one, and the smallest one. So it is seen that the transitions with the delta nu is equal to 2, 3, 4 have apparently, but not exactly 2, 3, 4 times of the frequency of the transition delta nu is equal to 1. In agreement with that observation, the observed wave number for the transition, for example, nu from the 0 to nu, means at the ground level to the 0 to some higher energy levels. Then this nu of z nu minus of z of naught. So for that, now okay, so I have from equation number 2 the z of nu of omega e, nu plus of this one, and this is square, then this g nu is equal to just expanding this one. Now this z0 means that this is the 0, then you have this omega e of 1 by 2 minus this is just a 0, then you have simply omega e xe 1 upon 4. Then now we have to find out this nu is equal to, that is the frequency, that is the wave number, this z of nu of the z0. Then just subtracting these one, so these two terms are cancelling out, these two terms are cancelling out, then you have this omega nu minus omega e xe nu square minus omega e xe or nu. And this must be equal to that, from that relation equation number 3, this z of nu, sorry, equation number 4, z of 0 nu minus z0 of 0. Then from here, once you are calculating from here, then you have this xe minus omega e x nu, and this quantity, you know that this quantity is equal to my omega 0, and this quantity is my omega 0 x0, omega 0 x0 from these two, equation number 5. So now finally I have the relation, that this is equal to omega naught, this must be omega naught nu minus omega naught x naught v square, and this omega e nu minus omega e x e v square. Thus the observed absorption frequencies in centimeter inverse give directly the positions of vibration level above the lowest level. The wave number separation between the two successive observation bands is given by, suppose this is the nu is equal to z, nu plus 1 and nu plus 2. Then the difference between this one, this is z, delta z of nu plus of half, delta z nu plus 3 by 2. The difference between this is the delta Z. Energy between this one, energy between this one. It means that this delta Z for this new transition between nu to nu plus 1 would not be same that the transition between nu plus 1 to the nu plus 2. So delta nu plus of half, this nu plus of half, the Z of nu plus 1 to the Z of nu. And once you are putting the same value, then you will be getting that this simply this omega e minus 2 omega e xe minus 2 omega e xe nu is equal to this quantity, because x, this omega e x is equal to, you have x omega naught x naught, simply. So as this nu increases, the separation between successive bands decreases. From this relation, simply, very nearly linearly it is decreasing in agreement with the observations what we are telling that. The second difference, once we will be calculating, that is difference between this energy level and this energy levels. Then you have this delta Z of nu plus 3 by 2 minus delta nu of Z of delta nu plus 1 upon 2. Then once you are estimating this one, then you will be getting that this quantity, just putting from this one, putting from equation number 7, then simply you can estimate this one from equation number 7. Then you have these quantities minus 2 of omega e xe, that is equal to minus 2 omega naught of x naught. So the second difference directly determines the anharmonicity constant, that is the anharmonicity constant. The values of omega e and omega naught are the obtained from the observed wave number of the fundamental band, which is given by this one. Fundamental band is given to you. Once the fundamental band is given to you, that corresponding to the first excited state, then from the G1 minus G naught, from there you can simply find out this constant. Once you know that since omega e and xe and omega naught and x naught have already been determined, and this omega e and omega naught can be evaluated from this expression. Thus we can determine the vibrational constant omega e and omega naught x e from the observed positions of the inverted absorption bands of the diatomic molecule. So once you have a fundamental one, that the first enarmonic, that is the overtones, then they are with respect to their positions, we can find out these enarmonicity constants. So this is all about this enharmonic, this diatomic molecule as an enharmonic oscillator. So for today's lecture, and I'm stopping over here, and in the next lecture we'll be discussing about the vibrational frequency and the force constant for the enharmonic oscillator and the isotope effect of vibrational rotator or vibrational spectra.